Hello viewers, welcome to this session. In our lecture series, we have reached last concept of first unit, that is Laplace transform. The last concept is unit impulse function or Dirac delta function. So today let us discuss unit impulse function, Laplace transform of unit impulse function and some examples. So when we see definition of impulse, here impulse is a force, extremely large force, which is applied in very short duration of time. So here that extremely large force is called impulse. If you observe an example in our day-to-day life, when you hit your finger or thumb with a hammer, you feel unbearable pain due to extremely large force which is applied in a fraction of second. Such type of force is called an impulse. So in study of bending of beams, you will come across point loads which is equivalent to large pressure acting over a very small area. So here when you see this example, here this is an iron or steel beam of length L. Here force is applied at a single point. This beam is supported at the ends by here these two red color supports. Okay, so here x-axis is taken along this beam and y-axis is taken perpendicular to this beam. Here y of x denote deflection of beam in the vertical direction. Okay, so this deflection satisfies Euler Bernoulli equation, which is EI into d power 4 y by dx power 4 equal to f of x. Here E and I are constants and capital F of x is force. When force is applied at a single point, then this force can be indicated by minus Fx into delta x minus a. Here this delta x minus a is unit impulse function, Dirac delta function, and this minus sign indicates this force is applied downwards. Okay, so whenever we are applying a large amount of force in a short duration of time at a single point, then that force is associated with this Dirac delta function or unit impulse function. Now let us define this unit impulse function mathematically. So if you consider a function capital F of t, here f of t is a function which is defined as 0 when time t is less than a, which is equal to 1 upon epsilon when a is less than this t is less than or equal to a plus epsilon, and again this function is 0 when t is greater than a. So this function is represented in this figure. So here time is taken on x-axis and this function f of t is taken on y-axis. Then when t is less than a, here there is no any graph, and when t is greater, here t is in between a and epsilon, then here this function is 1 upon epsilon. Okay, and when t is greater than a plus epsilon, again it is 0. So here this might be a plus epsilon. Okay, so whenever we consider a small duration of time, a to a plus epsilon, in this small duration, this 1 upon epsilon indicates impulse, unit impulse function f of t. Okay, so when this epsilon tends to 0, when this epsilon tends to 0, this width becomes very small. Then here epsilon tends to 0. So 1 by epsilon tends to infinity. So 1 by epsilon indicates a large amount of force when this epsilon tends to 0. So that means when this time becomes very short. So in very short duration of time, 1 by epsilon indicates a very large amount of force. So Here, as epsilon tends to 0 in the limit, the function f of t tends to be infinity at t equal to a and 0 everywhere. Okay, so when epsilon tends to 0, time t becomes a, t equal to a. So at t equal to a, 1 by epsilon is very large, that tends to infinity, and everywhere except a, this function is 0. Then f of t represents a force acting for short duration epsilon at time t equal to a. Then the integral, if you consider this integral, limit epsilon tends to 0, integral a to a plus epsilon into f of t, integral a to a plus epsilon f of t dt, which is equal to a, represents unit impulse at t equal to a. Okay, so here we have taken this integral 0 to infinity f of t dt, which is equal to integral a to a plus epsilon 1 upon epsilon dt, because here at 0 and at infinity, here f of t doesn't exist, only in the interval a to a plus epsilon f of t exists. That's why here we got integral a to a plus epsilon 1 by epsilon dt. When you evaluate this integral, here what do you get? 1 upon, here 1 upon epsilon is constant, integration of dt is t, a to a plus epsilon. So when you apply limits, 1 upon epsilon into a plus epsilon minus a. So a will get cancelled, epsilon will get cancelled. This gives 1. So when you evaluate this integral, we get 1. Okay, for all values of epsilon. Now, limiting form of f of t. So how can you define this unit impulse function? It is limiting form of this function f of t as epsilon tends to 0. So limiting form of f of t as epsilon tends to 0 is called unit impulse function or Dirac delta function. So Dirac delta function or unit impulse function is denoted by delta of t minus a. So delta t minus a indicates unit impulse function. So in very small amount of time, very short amount of time, here force, if force is very large, applied force is very large, then that is called unit impulse function or Dirac delta function. So here you can write delta t minus a in this manner. Delta of t minus a equal to limit epsilon tends to 0 f of t. Okay, here when a equal to 0, in our previous graph, here we have taken interval a to a plus epsilon. When this a becomes 0, then here you get like this, a to a plus epsilon, here 0 to 0 plus epsilon when a is 0. Okay, then unit impulse function at t equal to 0, here epsilon tends to 0, that's why here this width reduces. When this width reduces, then we get unit impulse function at t equal to 0, okay, here. So then here delta t can be written as delta t equal to limit epsilon tends to 0 f of t, because a is 0. Okay, where f of t equal to 0 when t is less than 0, 1 by epsilon when interval is 0 to epsilon, and 0 when t is greater than epsilon, like this. Here this is 0, here this is epsilon, like this. So f of t is 0 when t is less than 0 here on this side. Then in the interval 0 to epsilon, it is 1 by epsilon f of t. And when epsilon here when t is greater than epsilon, then f of t is 0. Okay, this is when a equal to 0. So here what is Dirac delta function? Delta of t minus a is called Dirac delta function or unit impulse function. So unit impulse function is nothing but a large amount of force applied in a very short duration of time. Now Laplace transform of Dirac delta function can be derived in this manner. Here f of s, we know f of s equal to L of f of t. Here given f of t is like this function. So here instead of small f of t we have taken given function f of t, which is equal to integral 0 to infinity e power minus st f of t dt according to basic definition of Laplace transform. But this f of t exists only in the interval a to a plus epsilon, we have seen. That's why here we have taken integral a to a plus epsilon, and in the interval a to a plus epsilon, this f of t, value of f of t is 1 by epsilon. So as 1 by epsilon is constant, we have taken it outside. So 1 by epsilon integral a to a plus epsilon e power minus st dt. Okay, now when you integrate this e power minus st, you get e power minus st upon minus s under the limits a to a plus epsilon. So when you apply these limits, 1 by epsilon into here 1 by epsilon into e power minus s into a plus epsilon upon minus s minus e power minus sa upon minus s. That is 1 by epsilon into e power minus sa into e power minus s epsilon upon minus s minus e power minus sa upon minus s. Okay, here I have opened this bracket and I have written this in this form, e power minus sa into e power minus s epsilon. Now if you write this minus sa by s outside, then what do you get? We have written e power minus sa by plus s outside. Okay, then here minus into minus, this becomes plus, then here you get 1. Otherwise let us write one more step in between. So this can be written as 1 by epsilon into e power minus sa into e power minus s epsilon upon s plus e power minus sa upon s. Here minus into minus becomes plus. Now if you take e power minus sa by s outside, here you get minus e power minus s epsilon, here plus 1. Okay, here 1 by epsilon take inside, so by epsilon. So here you get e power minus as by s into 1 minus e power minus s epsilon upon epsilon. Okay, now Laplace transform of, here capital F of t is nothing but delta of t minus a when you take limit epsilon tends to 0. So Laplace transform of delta t minus a equal to limit epsilon tends to 0 f of s, which is equal to e power minus as by s into limit epsilon tends to 0 1 minus e power minus s epsilon upon epsilon. Okay, now value of limit epsilon tends to 0 1 minus e power minus s epsilon upon epsilon is 1 by L'Hospital's rule. What is L'Hospital's rule? If you consider limit epsilon tends to 0 1 minus e power minus s epsilon upon epsilon, here we can't find value of this limit directly by applying epsilon equal to 0. When you put epsilon equal to 0, this becomes infinity. So we have to apply L'Hospital's rule. What is L'Hospital's rule? Before applying the value epsilon equal to 0, we have to differentiate numerator and denominator separately with respect to epsilon. So when you differentiate this numerator, you get limit epsilon tends to 0, limit epsilon tends to 0, here d by d epsilon of 1 minus e power minus s epsilon upon d by d epsilon of epsilon. Then what do you get? Limit epsilon tends to 0. Here derivative of 1 is 0. Derivative of this is, here we are differentiating with respect to epsilon. So here you get minus s into e power minus s epsilon. Okay, upon, here derivative of epsilon is 1. So what do you get? Limit epsilon tends to 0. Here minus into minus plus s into e power minus s epsilon. Now put epsilon equal to 0, which is equal to s into e power 0, which is equal to s. So here this whole thing becomes yes when you apply L'Hospital's rule. Then this s which is existing in the denominator and this s both will get cancelled. Then you get e power minus s by L'Hospital's rule. Okay. So Laplace transform of Dirac delta function delta t minus a equal to e power minus as. So using this definition of Dirac delta function, we can prove one more property. So that property is integral 0 to infinity f of t into delta t minus a dt equal to f of a. This is one property. I have not given proof of this property. We are applying this property directly in solving our examples. Okay. So here we have discussed Laplace transform of Dirac delta function delta of t minus a, which is equal to e power minus as. Okay, e power minus as, and this property integral 0 to infinity f of t into delta of t minus a dt equal to f of a. By using these two definitions, we are going to solve these examples. So let us solve these examples one by one. First example is integral 0 to infinity e power minus 4t delta t minus 3 dt. Delta of t minus 3 dt. We have to evaluate value of this integral using this property. So what is that property? We know that property integral 0 to infinity f of t, not e power minus st, f of t into delta of t minus 3 dt, which is equal to f of a. Okay, here not 3, let us write general terms. Delta t minus a, delta of t minus a, f of t into delta of t minus a dt equal to f of a. Now let us compare this given question and this LHS of this property. Then you can identify f of t equal to e power minus 4t and delta of t minus a is equal to delta of t minus 3. Right? So here from this you can write a equal to 3. A equal to 3. Now here f of t equal to e power minus 4t. So we know value of a. Now replace this t by a. Here f of t equal to e power minus 4t implies f of a equal to e power minus 4a, which is equal to e power minus 4 into 3, which is e power minus 12. Okay, therefore integral 0 to infinity e power minus 4t into delta of t minus 3 dt equal to f of a. What is f of a? E power minus 12. E power minus 12. This is solution of this question. Very simple. First you have to identify f of t and value of a. Then using this property you can find f of a. So f of a will be the solution of this. Now let us see next question. Integral 0 to infinity phi of t into delta dash t minus a dt. Evaluate integral 0 to infinity phi of t into delta dash t minus a dt. Here this is not delta of t minus a. This is derivative of Dirac delta function or derivative of unit impulse function. So here we have to apply integral uv rule first. So integral uv equal to u integral v minus integral of integral v into derivative of u. Let us apply this formula. So if you apply this, here consider this as u and this as v. Then this is equal to phi of t u into integration of delta dash of t minus a dt under the limits 0 to infinity minus integral 0 to infinity. Here integration of this. What is integration of this? Integration and derivative will get cancelled. You get a delta of t minus a into derivative of phi of t, that is phi dash of t dt. Okay, now this is nothing but phi of t. Here integration and derivative, that will nullify. You get delta of t minus a under the limits 0 to infinity minus integral 0 to infinity phi dash of t into delta of t minus a dt. Okay, so here in this term, whenever this upper limit, when t equal to 0 and t equal to infinity, Dirac delta function is 0. That's why first term becomes 0 for both upper and lower limits. Then you get, which is equal to 0 minus integral 0 to infinity phi dash of t into delta of t minus a dt, which is equal to minus integral 0 to infinity phi dash of t into delta of t minus a dt, right? This is similar to the property which we have mentioned, integral 0 to infinity f of t into delta of t minus a equal to f of a. So according to this property, we can write this as this one, since this is equal to this. Here integral 0 to infinity phi dash of t into delta of t minus a dt equal to, here you can take minus sign also, equal to minus of, according to this, this is equal to f of a. But in the place of f of a, here phi dash of t is there, and in the place of a is there. That means here a is not given some other number, a is same. So on the right hand side we get phi dash of a. Therefore integral 0 to infinity phi of t into delta dash of t minus a dt, given question, equal to minus of phi dash of a. This is solution of second question. Now let us see third question, that is find Laplace transform of t cube delta t minus 5. Find Laplace transform of t cube delta of t minus 5. Now to solve this question, before applying this property, we have to apply basic definition of Laplace transform. So Laplace transform, basic definition of Laplace transform is L of f of t equal to integral 0 to infinity e power minus st f of t dt. So according to this definition, Laplace transform of t cube into delta t minus 5 can be written as integral 0 to infinity e power minus st into t cube into delta of t minus 5 dt. Now consider these e power minus st and t cube in a single bracket. Then this is similar to LHS of given property, right? So here integral 0 to infinity e power minus st into t cube we have taken in one bracket, and delta of t minus 5 in other bracket dt. Now this is similar to integral 0 to infinity, here f of t into delta of t minus a dt, which is equal to f of a. Now compare LHS of this and this term, then what do you get? F of t equal to, compare these two and compare these two. So f of t equal to e power minus st into t cube and a equal to 5. Then find f of a. Put t equal to a. F of a equal to, put t equal to a. Then you get e power minus sa, which is equal to e power minus, even t cube is there. So e power minus sa into a cube, which is equal to e power minus s into 5 into 5 cube, which is equal to 5 cube is 125 into e power minus 5s. Okay. Therefore, integral 0 to infinity e power minus st into t cube into delta of t minus 5 dt equal to 125 into e power minus 5s. This is nothing but Laplace transform of t cube delta of t minus 5, which is equal to 125 into e power minus 5s. Now let us move to fourth example. Fourth example is find Laplace transform of cos t into log t into delta of t minus pi. Laplace transform of cos t into log t into delta of t minus pi. Now as usual, let us write basic definition of Laplace transform. L of f of t equal to integral 0 to infinity e power minus st into f of t dt. So, L of cos t into log t into delta of t minus pi can be written as integral 0 to infinity e power minus st into cos t into log t into delta of t minus pi dt. Now let us write all these terms except this delta term in one bracket. Now this is similar to the LHS of the property integral 0 to infinity f of t into delta of t minus a dt equal to f of a. Now compare these two. Here f of t, this is f of t. Okay. So f of t equal to, what is f of t now? E power minus st into cos t into log t. Right? Now a equal to pi. When you compare these delta terms, you can find a equal to pi. Now what will be f of a? F of a equal to e power minus sa into cos a into log a. But a equal to pi. So which is equal to e power minus pi s into cos pi into log pi. Value of cos pi is minus 1. So e power minus pi s into minus 1 into log pi, which is equal to minus of e power minus pi s into log pi. Right? So therefore here integral 0 to infinity e power minus st cos t into log t into delta of t minus pi dt equal to e power minus s pi into cos pi into log pi, which is equal to minus e power minus pi s into log pi. This is solution of this question, fourth question. Now let us see fifth question. Fifth question is find Laplace transform of delta of t minus pi upon t. Delta of t minus pi upon t. Laplace transform of delta of t minus pi upon t. So as usual, this can be written as, this is equal to integral 0 to infinity e power minus st into delta of t minus pi by t dt according to basic definition of Laplace transform. Now this can be written as integral 0 to infinity e power minus st by t into delta of t minus pi dt, right? That means we have written all the terms except this delta term within a single bracket. Now this is similar to the property integral 0 to infinity f of t dt, integral 0 to infinity f of t into delta of t minus a dt equal to f of a. Now compare LHS of this property and this integral. When you compare, you can find f of t equal to e power minus st upon t and a equal to pi. Then f of a equal to e power minus s a upon a. Okay, but a is pi, which is equal to e power minus s pi upon pi. Therefore, Laplace transform of delta of t minus pi upon t is nothing but e power minus pi s upon pi. Now let us see next question. Last question, sixth question is, find Laplace transform of e power minus pi t into delta t minus a. Find Laplace transform of e power minus pi t into delta of t minus a. Now as usual, write in the basic form of Laplace transform, that is e power minus st into the whole thing which is given in curly bracket, that is e power minus pi t into delta of t minus a dt according to basic definition of Laplace transform. Now write these terms within one bracket. Now according to the property integral 0 to infinity f of t into delta of t minus a dt equal to f of a. Now write f of t by observing this. So f of t equal to e power minus st into e power minus pi t. Okay, and a is a only, no change, a equal to a. Now f of a equal to e power minus sa into e power minus pi a, right? But a equal to a only, so f of a equal to this much. So you can add these powers because bases are same, minus sa minus pi a. If you take minus a common, you can get minus of s plus pi into a. Therefore, Laplace transform of e power minus pi t into delta of t minus a equal to e power minus of s plus pi into a. So here in this session we have discussed basic definition of unit impulse function and Laplace transform of unit impulse function and its applications, and again we have solved 6 examples on this concept. So now first unit Laplace transform is completed. Now in next session we are going to begin second unit inverse Laplace transform. So let us meet in next session. Thank you.